After understanding the transmitter side, today we focus on the receiver, the heart of reliable 5G performance. Receiver sensitivity, blocking, and coexistence determine whether your signal gets through cleanly or disappear into the noise. Receiver sensitivity defines the weakest signal a device can successfully demodulate. It depends on thermal noise, bandwidth, noise figure, and the required signal-to-noise ratio for a given modulation. In 3GPP tests, reference sensitivity is measured using standardized setups, typically around -96 dBm for 20 MHz new radio channel in FR1, depending on the MCS. And this is the formula to calculate the receiver sensitivity. -174 dBm is one of the most important numbers in RF engineering. It represents the thermal noise power density at room temperature 290 K in a 1 Hz bandwidth. A receiver's noise figure quantifies how much noise it adds internally. Good design minimizes noise figure, improving weak signals performance. But linearity is equally important when strong neighboring signals are present. Third-order intermodulation distortion can corrupt desired channels. And this is one of the receiver performance of intermodulation I tested before. 3GPP defines blocking and intermodulation performance tests to ensure UE survive in dense RF environments. Blocking measures performance when an unwanted strong signal appears nearby. IM3 test checks distortion when two tones mix and fall into the receiver band. Typical limits ensure only minimal degradation. For example, less than 3 dB throughput loss under strong adjacent signals. And this is the desired carrier, a weak signal, and this is a blocker at the adjacent channel, one channel away from the center frequency, and this is another alternate blocker. The alternate blocker is 2 or 3 channels away from the center frequency, and this is after the filter rejects most of the power of the blocker here, and then the filter rejects most of the power of the another blocker here. So the blockers here are lower than the desired signal. In 5G smartphones, multiple radios, 5G, Wi-Fi, GPS, Bluetooth, coexist in tight spaces. Poor isolation or harmonics can cause receiver desense, reducing effective sensitivity. Designers use filtering, antenna isolation, and then time domain coordination to minimize these effects. Receiver design challenges differ between FR1 and FR2. In FR1, thermal noise dominates. Antennas are omnidirectional. In FR2, beamforming boosts gain, but the blockage and calibration are critical. FR2 receivers often use analog beamforming and calibrated phase shifters to achieve directional gain. Key 3GPP defined receiver metrics include reference sensitivity, dynamic range and linearity, blocking and intermodulation, coexistence, Desense testing. Together, they ensure the receiver can detect the faintest signals, even in crowded spectrum. In 5G, receiver performance defines the real-world coverage edge. Good sensitivity and linearity keep your connection strong, even in harsh conditions. In the next episode, we'll explore spurious emissions and coexistence, how transmitters avoid interfering with other systems. And that's all for today. If you like this video, please subscribe, share, and like. Thank you.